Hi everyone. So today we get to start a new chapter, chapter 5 in Thompson, specifically the first section, which is going to be on first and second order perturbation theory. Don't let that name scare you or anything like that. It's just you're going to be taking it through this one step at a time in order to figure out how we can actually utilize what we learned last chapter in chapter 4 from the Dirac equation, right, which turns everything into these 4x4 matrices, and then the states are actually spinors. And what we're going to do is we're going to try to, well, not try, we are going to, right, translate that into these transitional matrices that we learned from chapter 3. I guess I don't have to do that little arrow thing. TFI, where this transitional matrices, right, multiplied by the density state, and this density state actually turns into these integrals of delta functions. So we don't have to go into detail about that right now. And that allows us to calculate this thing called gamma Fi, right, which is the transition rate from some initial state to some final state. Okay, and remember this is called Fermi's golden rule. Okay, and so the reason we did the Dirac equation before is because the Dirac equation actually describes the interactions of electricity and magnetism, and this is actually the simplest case. The entire framework is called quantum electrodynamics. You may have heard me say this once in a while and then not even explaining what it is. So here we're actually going to be looking at quantum electrodynamics and actually having a full description on how we actually utilize QED in order to describe interactions of electrons, muons, photons, taus, those type of particles where they're scattering off each other only through the electromagnetic interaction using the photon. Okay, so let me fix my screen. Move this over here. Okay. So, but before we can do that, what we're going to do is we're actually going to do the first and second order approximations of these interactions, because the higher order actually will be increasingly, or actually more accurately, decreasingly significant, and therefore we actually only need to do the first and second order approximation of these interactions. Okay, so this TFI thing, right, which is the transition matrix elements, okay, are these brackets of initial and final state, and through this V now is actually what's known as the interaction potential. Okay, so let's just write that down. Right, it's the interaction potential. Okay, and we'll give a classical version of this as an example. Okay. But this is actually only the first order right here, right? The reason it's first order, there's only one V involved, okay? And then this, I describes the initial state that the particle is in, and F is the final state the particle is in, okay? And then what we do is then we add up more of these, okay? So this is the second order approximation, or the second order perturbation, where now, right, this has two V's in it, okay? And then in order to get the right units, we're also going to divide by the energy, because the potentials also have units of energy, okay? Where the initial and final state, let me erase this stuff, right? So this is the initial, this is the final state, is mediated by some intermediate state, state, okay, J, okay, I and F. I know J is not between I and F, but so hopefully this J is just some index that we're gonna carry around. Okay. So let's just talk about the second term real quick, right? The second term, like if you want to think about it physically, is that, let's say, well, I'm gonna draw my own diagram because it's pretty easy to draw, right? Let's say you have some initial particle coming in, okay, and it has some interaction, okay, right? Maybe it's an electron, therefore it emits some photon, okay, and that this photon is actually this intermediate state. This is the initial state, Okay. All right. Actually, let's draw this like this. Sorry, instead of thinking about this as a photon, let's draw this as some intermediate state of this particular particle, because we're not actually thinking about the emission yet. Okay. And so there's this little kink here, right? This kink is due to, maybe another electron that's repelling this initial electron away from it, right? So we can think about this as some potential VJI. Okay. Oops, let's do a capital V there. Right. And then it interacts again, right, into its final state. Okay. F. Let's go over here. Okay. Then this will be VFJ. Okay, because we're transitioning from I to J initially, and then we're transitioning from J to F on the second time, and therefore it actually creates this kind of intermediate state between the initial and final. Okay, so that's what the second term is. Okay, this first term, right, is actually just, we're going to do some examples of this. It's just the particle, scattering directly from its initial to final state. Okay, and then so we actually denote that potential as just VFI. So let's think about how to interpret these. Initially, let's go back to classical mechanics. Okay, where, right, these things happen if, like, maybe an electron is flying through the air. There's another electron, right? Let's call this E1, E2. Okay. The way we think about it in introductory physics, right, is that, well, this electron is giving off some electric field, right? Since it's a negative charge, the fields will actually point towards the electron. Okay. Okay. So when electron 1, let me draw this closer, enters this field, right, it feels a force. Let's draw the force in green. Green, right, in the opposite direction of electric field, because electrons follows the opposite direction of an electric field, right? In that case, right, this electron will get scattered off, right, bounce off the other electrons, right, into the same electron, but this is the initial state and this is the final state, right? Minus. Okay. So this is a very similar picture to up here, but then, instead of thinking about it in terms of the potential, we can think about it as an electron. Okay. So also in in introductory physics, what happened is that, well, instead of thinking about this as an electron emitting some electric field, right, what we do afterwards to make things simpler is to instead think about this as some electric potential. Let me draw that in blue, right? Right, V, the electric potential. Ooh, I'm not going to be able to remember what the equation is. It's like 1 over 4 pi epsilon naught, right? The charge divided by 1r, I think. Okay, don't quote me on this. Okay, okay. Where this electric potential is kind of like a equal value, but then center around that charge still, right? Where this is some potential, negative 10 volts, negative 5 volts, negative 1, and so on like that. Okay, and then so this potential, right? So we're getting closer to this, right? Right, is by applying conservation energy, right? So there's some energy that's being converted. So it has some kinetic energy initially, right? And then in this point, right, it has both kinetic energy plus potential energy, right? And then the outgoing particle have all kinetic energy, right? So this is a way to also think about how an electron interacts with another electron, which is giving off an electric field, electric force, electric potential, right? All of them are just different ways to describe the same thing. Okay, so the problem is that if you try to do this from the framework of quantum mechanics, the book writes that is unsatisfactory. Okay, it's like a really mean thing for a professor to say to a student, right? Let me do a, can I do a red pen here? Let's do a red pen here. Okay, so one of the problems is that, you know, if you have just two electrons sitting around, right? So like E1, E2, right? There's nothing exchanged between them, okay? So in this classical framework interpretation, right, you have an electron coming in, it never touched the other electron, right, and then it just flies off in the other way, okay? It never actually touched each other, right? So there's actually what's known as a mediator between the particles and the field, and then with QED we're going to find out that the mediator is actually photons, which is stuff we see every day. Okay. The force also acts from the field instantaneously, meaning that as soon as this electron enters the electric field or the electric potential, right, it has an immediate effect on this electron, which doesn't make sense. So because let's say, you know, someone is, you know, trying to play a trick on you and just, you know, make that electron disappear, right? And then you're flying along with your electron, right, thinking there's no field, right? But then they turn on that electron. Okay, it's hard to do in real life, but let's just say that happens, right? And then all of a sudden that field appears, and then the electron instantaneously gets affected by it, which doesn't make sense in relativity because, right, the electric field should take some time in order to get to the electric field from electron 2 should take a little bit of time in order to reach electron 1. Okay, so and this is even more disturbing, right? Because if you put an electron somewhere in the universe, right, put E2, right, somewhere in the universe, this field, right, this electric field, which is actually pointed the other way, right, affects the entire universe, right, effectively, right. So me moving an electron on Earth, right, in this classical way of physics, right, affects, you know, charges that are moving around, you know, tens and hundreds and millions and billions of light years away instantaneously, and that makes no sense, right? In the context of special relativity, where it takes light, you know, tens and hundreds and millions and billions of light years of distance, years, in order to reach, you know, these charges that are, you know, billions of light years away. Okay, so in quantum mechanics, what we're going to do is we're going to describe this using perturbation theory instead, where we're doing the first and second order only, but right, this will apply with higher and higher order perturbation. And this entire framework is actually known as quantum field theory. We're not going to learn quantum field theory. And in fact, in this context, we should think about this as more like quantum particle theory instead, because we're not really going to deal with the fields that describes these particles. So the name field is not exactly like electric field, but I don't want to dive too deep into it. But yeah, the field actually could be thought of as the more fundamental thing than particle in it. But in this class, I think so far we're going to be doing quantum particle theory. Okay, so let's just think about how we can describe interactions between particles where the forces are actually just particles being exchanged between the two, and there is no force. Okay, I guess the quote is actually there is no spoon, but there is no force. Okay, so the interaction, what we want to think about in these interactions is that an electron coming in, right, electron 1, okay, and what we're going to do is we're going to draw this in these time space axes, right? So time goes along the right, space kind of goes vertically. Oops, why did it erase? I don't know why. Someone typing something? Sorry. Oh, okay, I see what it's doing. I think it's thinking that I'm trying to write L's. That's why it's doing that. Okay. So I'll try not to do that. Okay. Okay. So this is time. This is this is a pendant that converts to words directly. Okay. All right. Time, space. Let's call it x or something like that, right? Okay. And we have some particle coming in. Let's just ignore that -1 for now because that was not on purpose. Right. And then what happened is that this electron 1 fires off a photon traveling at the speed of light, and then it gets intercepted by another electron, right? When it emits this electron, right, it has, in order to conserve momentum, right, it will go off in this way, kind of, so that, the original momentum is conserved this way. Okay, this is let's call this, initial state, right, A. Okay, let's call this after state C. Okay, and then this intermediate particle doesn't have to be a photon. We're just going to call it some X. Okay, and it's this intermediate mediating photon or particle X, right, gets captured by another electron / another particle, just in general, B, right, and by getting stuck to it, right, what happened is that, right, the particle B also scatters off in a new direction afterward. Okay, and that's what these diagrams are trying to denote to you. But there is 2 different diagrams here. Okay, the one I drew, make sure that I flipped the A's and the B's, sorry about that, right? The one I drew is similar to this one, but I just flipped the A's and B's, where, right, a particle comes in, right, it's the one, and then A is the one that emitted the photon or this X particle. The reason I draw this squiggly line is because this represents a spin 1 thing, but in this case it's just a general particle. It doesn't have to be a particular spin. In fact, we're gonna, I think about this in terms of scalars at first. Okay, so this little point here, right, is where particle A emits a X and scatters off into a new direction C, right? So these could be the same particles, electron, and this photon, right? This point here, the vertex here, right? Now we can think about this V, instead of thinking about it in terms of potential, we can think about this as some vertex, right? And it's going from some initial state to some intermediate state, J, in the middle here. Okay. Okay. And that shoots off a particle, whatever that is, right? And then B particle comes along and gets struck by this X particle. Okay. We can say electrons and photons, but with just to be general, we don't have to. Okay. And this interaction also is another vertex, right? You have another crossing point where the particle X collides with particle B, and then therefore it changes its momentum into a new momentum D. Okay, so this is the initial state, and then we have basically the intermediate state is actually this broad spectrum part here, right, J, and then the final state is what actually comes out. Okay, so in reality we only see the initial and the final. Okay, another thing that could happen is that, right, instead of particle A emitting the photon, we can think about particle B as the one that emitted the photon. And let me just go through this, and we'll see why we cannot tell the difference between the two. Particle B emits the photon, right? To conserve momentum, it's going to go off in a new direction D. Okay, and this particle, they're going to call it X tilde, so it could be a different particle. Okay, goes off and strikes particle A that's also in, coming in, and particle A goes off into a new direction. Sorry, a particle with momentum A goes off in a new direction with momentum C. Okay, that was a lot of words. Okay, once again, right, we have some initial state, right? Let's just point to it here. Okay, right, we see this, okay? But there's also some intermediate state, right, that we actually don't see, right? Unless we can intercept this intermediate particle and catch it, we actually don't know if it's an X or X tilde, right? But what we do see is these, particles with new momentum coming out, C and D, okay? So the initial and the final and this intermediate, right? So what we really see in a laboratory, we see only the initial and the final state, and we don't see the intermediate, okay? Okay. So in the case, in order to account for both of these possibilities in quantum mechanics, okay, basically what's known as, if we did quantum mechanics, what we'll do is that we actually have to sum up, let's say, this, let's call this I think there's a name for it. Yeah, A, B, F, I. Let's see. Yeah, they actually don't have a different name for it. Okay, so what I'm going to do is actually kind of tell you how to think about this. So each of these has some interaction amplitude, or this matrix element, TFI thing, right? But these are different matrices, right? So let's call this with a little squiggle on top. So in quantum mechanics, in order to account for the probabilities for both of these to happen, okay, and remember, probability is basically going to be proportional to the square, right? But instead of squaring them first, what we have to do is actually we have to add these different transition amplitudes or matrix elements, and then we square it. So this is where we get quantum interference effect. Don't worry too much about it. So whenever we have to do that, we will explicitly tell you that it happens, okay, just as in this case. Okay, so what I'm going to do is we're going to describe, I think with the first one is going to be X, the initial state. Okay, yeah, we're going to describe this one first, the one on the left. Okay, so this is the matrix element that describes the left diagram. Okay, okay, so let's go through all this little stuff in here. Okay, so the transition of A and B from its initial to final state, okay, both of these particles from some initial to some final state, okay, okay, is this bracket, right, thing where you have some initial state and you have some final state at the end, but then there's some intermediate state here, right, which is denoted by this J, okay, and then in order to get the units right and also conserve energy, what we do is we actually have to divide that by the difference in the energies of the initial and final states. Sorry, the initial and the intermediate states. Okay, and that factor is going to play a role in a second, towards the end here. Okay. Okay, so what is this little piece here, right? This initial and this intermediate, right? Okay, so this initial state, remember, that's particle A, right? Okay, and it's interacting with some potential VFI here. Let me do a different color, right? Oops, pointed to the wrong place. The intermediate state, J, right, has both particle C and particle X in it. Right, let me just, right, because the C particle is actually here already, right? It existed. C here, right? So at this stage, you have both particles C and X at the same time. So therefore, this intermediate state, let's do that in green. Nope, don't like green, green. Right, this intermediate state actually is a combination of both particle C and this X particle. And if that's bothering you, just think about A as an electron, C as the final electron, and then the final electron 1, and X is the photon between them. Okay, right? And to get to the final state, right, which is going to be this particle D, okay, which makes it to this side here. Similarly, in the intermediate state, let's see over here, right, both particle X and particle B exist at the same time, so therefore, right, this the right hand side of this transition matrix, which is the ket part of from our bar ket notation, but don't worry about what the wording means of that. It's just in case you hear that in the future. Okay, will be X plus B. Okay, well, the initial energy, right, is whatever the initial energy of A and B particles are, right, those two electrons. The final energy, sorry, not the final energy, the intermediate energy is the sum of the C particle's energy, because C exists here, the X particle energy, X exists here, right, and B particle, because B also exists here. Okay, we're just tracking a lot of these energies to make sure we're accounting for all of them. Okay, so X plus B and X plus C are these virtual states, and just to make sure people are clear on that, because that gets confusing sometimes, is that in these virtual states, the system could borrow energy from the vacuum. Meaning what's going to happen is that, for example, let me just give an example here. This is not electrodynamic, but it's actually the weak interaction. But we already have examples of this where you have a muon, right, and it decays, right, let's say through a W boson. This goes to a neutrino, right, and this decays into, let's say, an electron and a electron antineutrino. Okay, so the particleness actually goes this way, goes this way, go this way. Okay, the mass of the W boson is 91 GeV. The mass of the muon is 0.106 GeV. Okay, right? So the muon actually does not have enough rest energy to make a W boson ever. But since the W boson in this case is actually a virtual particle, right, what's happening is that this decay is actually borrowing some energy from the vacuum temporarily for a very, very, very short amount of time. How short? Okay, that amount of time has to obey the energy uncertainty principle, where the amount of energy you borrow from the vacuum, okay, times the amount of time you borrow that amount of energy has to be, well, this book uses approximately h bar, but in a lot of textbook you're going to see the uncertainty principle written as just an inequality. This has to be less than or equal to h bar over 2. Okay. So if that W boson exists for a short enough of time, you can borrow enough energy from the vacuum in order for that decay to happen. Okay. Right. So this V here, let's go over here, right? Right. This V, right? Interaction. This V part describes the interaction between the initial particle to the intermediate particle from between A and this, X plus C, right? And this is the, what we can think about as kind of like the potential that actually of those two interactions, for that interaction to happen. Okay, and right, this part here is the interaction that describes this intermediate state of from the intermediate state to the final state from X plus B, right, which is the first half of the diagram, into the D state, which is the second electron basically going outward. Okay, so this is the outgoing electron, this is the incoming electron. Okay. Okay, one of the things that we want to remember is that these TFI things are not Lorentz invariant. Okay, and this was in chapter 3, right? We fixed this by defining a new thing, okay, the Lorentz invariant matrix element, MFI, okay, just more letters, okay. This is, I copied this equation out of chapter 3 by just multiplying TFI by 2 times the energy, well, the square root of 2 times the energy of all the different particles that's involved in our interaction, okay. In this case, instead of E1, 2, 3, 1, 2, A, B, these E's are actually going to be A, B, C, D, okay. Okay. So we can do the same thing, right, and convert these VJI to MJI, okay. Okay. But what we're going to do is we're going to convert this, okay. So this VFI would have VJI up here, okay. Sorry, I always forget this intermediate one, okay. All right, remember it's this matrix element calculation of whatever the initial state is through that potential, right, to this intermediate state where you have both the C particle and the the intermediate particle, okay. And just by dividing both sides by 2 times all the particles that are involved, so in this case, right, involves the particle A, particle C, particle X, right, 3 of those, and then square root that whole thing with this power of 1/2, right, you would convert this to these MJI, but just to be more specific, right, this is the matrix, Lorentz invariant matrix element for transitioning from the particle A to a state of particle C and X, right, combined together, okay. Okay. And this M thing is known as the Lorentz invariance matrix element, okay. I just created this shorthand line. I don't think other people use it, but it's kind of nice. So if the particles are scalars, okay, meaning they don't have any spins, the stuff we deal with last chapter, this matrix element is actually can be quantified by a scalar, right, by a number. This is a scalar, okay, and this number can be measured by some experiment, and once you measure it once, you know what that interaction matrix element is, then you don't have to then you can use it in your calculation. So in this case, let's just call this number GA. This could be a complex number, but it's just still a scalar, so that you don't have to deal with any matrix multiplication or anything like that, okay. So for the vertex between A, X, and C, right, let me redraw this down here so that we see this, okay. Where the interaction is, you have the A's on top, right? Yeah. You have some A particle coming in, some particle with some A momentum coming in, right? And it's spitting off some X particle. Yeah, I'm doing the photon already, which is not necessarily true. Okay, let's get off some B. This is some particle X. Oops, I think this is particle B. This is C. Okay. D, right? So in order to account for this, right? Oops, where did I point this to? Right? This interaction of A, right, C, right, and X together, okay, it's going to be some scalar for this simplify idealized case that if the particles are scalars, meaning there are spin, that these particles has no spins, okay, this matrix element would just be some constant that you can measure, right, and they call it GA, okay, and this GA, right, has to be divided by all these energies, square rooted, because there's 3 particles involved, okay. So that's our first interaction matrix element. Okay, the other factor, right, is where we have particle D, which is the final state here, right, and then the intermediate particle X, the particle B also exists here. So at this point, right, there's three particles involved, B, D, and X. So it's basically X combining with B to make it into particle D. Okay, and that has some interaction potential. And if the particles are also scalars on the other side, right, this will also be just a number. Okay, and let's call that GB just in case those are different. Okay, and once again we have to divide by the square root of 2 times the energy of all the particles involved. Okay, so putting all this all together, okay, right, so we have this piece, right, VJI, okay, which is this part here. We have this piece, VFJ, which is this piece here. Okay, you put them all, well, there's still this energy stuff that's all happen to be on the bottom, but if you put them all together, okay, you're going to get 1 over 2 times the energy of the intermediate particle, all four incoming and outgoing momentums. Okay, square root it. Okay, and then of course, since you have two factors GA and GB here, you get both these factors here. Okay, and then we still have this EA minus EC minus EX on the bottom. Okay, so to convert this from TFI to MFI, remember this is the Lorentz invariance matrix element line. Okay, we also have to divide the TFI, basically if you divide both sides by this big square root, right? Actually, no, you don't. If you want to convert to MFI, you just multiply it, right? Yeah, you just multiply by all the incoming particle energy. It basically cancels out this factor on the bottom, which is really nice. Okay, so MFI is actually just 1 over 2 times the energy of the intermediate particle, the two coupling constants, okay, for a scalar. This is once again only for scalar interactions, okay, divided by the energies of A, C, and X subtracted from each other. Okay, so note that, yeah, this EX, right, this EX thing, right, is able to borrow energy from the vacuum for a short amount of time. But the thing is, right, no matter what, the energy, the Einstein energy momentum relation still holds. So whatever EX square is, right, it's going to be equal to its momentum square plus its mass square. Okay, so that's the first diagram where, right, where you have particle A shooting off. I'm going to write the squiggly line because it just makes it easier to see on when I'm writing it, right, shooting off some particle X, right, and then we have particle B scattering off that. So that's this diagram. Okay, right. The second time order diagram, right, is where particle B is the one that fires off the X, well, we're going to call it X tilde just in case they are different particles, and strikes A, and then they go off into new momentum C and D. Okay, okay, we go through the same process and calculate the Lorentz invariant matrix element once again, right? Okay, what happens is that this will be labeled MBA, okay, because B is the one that emitted the photon first, where the other one is MAB, because in that case A is the one that emitted the X particle first. Okay, sorry if I'm mixing X and photon, because it's gonna turn out in this case going to be, when we get to the end of this chapter, it's going to turn out to be the photon. Okay, right, it looks very similar, right? In fact, you can probably figure out what it is by just replacing wherever you see A and C, you replace it with B and D, basically. Okay. Okay. right? Since both of these processes are possible, as I mentioned in the beginning, we're going to add both of these processes before we square them, okay, to find the probability, okay? And I know that those of you who didn't have quantum mechanics yet, maybe mixing up what does he mean by amplitude? Why is he talking about amplitude when he's talking about matrix elements? So these matrix elements are the amplitude of these interactions, okay? Okay. Right, so what we want to do is add MAB with MBA, okay? So if you copy down those equations from the top, you can factor out the GA and GB and then the 2x, right? And then you have to do the subtraction between, sorry, the addition between the parts that are not common between the two, which is the energy in these denominator, right? A, C, B, and D. Okay. But what we can do is we can use conservation of energy, right? The incoming energy A plus the incoming energy B, right? So let's just draw that, right? A. So A has some incoming energy, B has some incoming energy, right? Whatever comes out of C and D, right, also have to have the same energy, right? Energy plus C, energy D, okay? What we can do is then we can solve this for EB minus ED, which is exactly what we have here, right, in terms of EA and EC. If you do that substitution here, now you have a common denominator, well, almost a common denominator between them, okay? Except the sign of x got changed, the EX got changed. Oh, because you're doing a subtract, you flip this from an addition to a subtraction, okay? Then what you do is you do a little bit of factoring, and you can actually factor out EA minus EC squared minus, and this turns into, and then minus EX squared, okay? And then that, all of that is still underneath GA times GB, okay? And then, so I think you can also multiply in these factors here, okay? Since the momentum at each vertex is conserved, so remember that that if you have a particle A coming in with some momentum PA, 3 momentum PA, right, and it spits out a particle PX, right? Say it was going this way, okay, PC, right? Okay, the momentum of PX is going to be the difference between these two momentums, right? Okay. Once again, we can use the Einstein energy momentum relation. We use this equation a lot, okay? Where if we put in Px in here, okay, Ex squared is actually equal to the difference in the 3 momentum of particle A and C squared, okay? Not so bad so far. We still have this mass square term at the end. What we can do is then we can substitute in Ex squared up here, okay? Okay, right? Then what happens is that you get Ex squared down here, okay? Because, and this is a subtraction between the two, so that's why you have 2 negative signs here, okay? And then the difference between EA minus EC minus the 3 momentum PA minus PC, right? This whole thing, right, is actually the 4 momentum square, okay? Let me just write this out to be clear, okay? So remember that momentum mu A, right? If we subtract that with the 4 momentum C, right? Oops. That's equal to whatever energy A is minus energy C, okay? And the second component of that, well, let's just, I think hopefully it's okay for me to write the 3 momentum of this, right? Like this, Okay, that's what this 4 momentum is, right? There's 1 component here and 3 components here. Okay, but then, right, if you were to square to calculate this, right, what you would do is you have P mu A minus P C mu. Okay, and then P the downstairs A minus P mu downstairs C, right? In that case, what happened is that, right, this downstairs one had the same thing, but you have the negative of this instead. Okay, so if you multiply these two together, you get EA minus EC, the whole thing square, right? Because this is the 0th component. Okay, this is mu equal to 0. Okay, and then you have to subtract because you're going to flip the sign of this. Let me just write that out explicitly so we see it together. Mu A minus P mu C, right? Whereas downstairs was the covariant. The energy part stays the same, but then the momentum gains an overall negative sign, right? The 3 momentum gains an overall negative sign. So if you multiply these two together, you get minus PA minus PC, 3 momentum squared. Okay, and that's exactly what we have here in this box. Okay, so in the shorthand notation for this, right, just as P mu equals to P squared, unfortunately, right, you have to know whether this P is actually 3 momentum square or the 4 momentum square. So this one is actually the 4 momentum square. Okay, so that's equal to PA PC 4 momentum squared. Okay. In fact, we're going to skip that also, even shorthand a little bit longer. We're going to define PA, oops, that's a C there. PA minus the 4 momentum, the difference in the initial and final momentum squared, 4 momentum squared, we're going to call that Q. Okay, where Q is actually the 4 momentum of the particle exchange between them, called the virtual particle. Okay, a lot of places you will also see Q as the I think it's called the propagator's momentum. Okay, oh, we're going to talk about this in a second. Okay, propagator's momentum. Okay, it's basically the momentum of X. Okay, the 4 momentum of that particle X. Okay, so this simplifies this MFI thing for scalars at least. Okay, so this all still we're dealing with scalars. Okay, where MFI is just these coupling constants, right, divided by Q squared minus the mass of the particle, this inner propagator particle squared. Okay, the term 1 over Q squared minus M squared is known as the propagator itself. Okay, right, and this factor is Lorentz invariant to begin with, right? Because 4 vector squares are always Lorentz invariant, right? Mass is just a number, so that's always going to be Lorentz invariant. So this propagator factor, right, is going to be useful even in the future, even when we're not dealing with scalars, because, right, when the assumption of dealing with scalar gave us these GAs and GBs, but in the future, when we get to spin 1/2 particles, we're going to change these GAs and GB out, but this propagator still remains. Okay. So